So let me talk about that, what we need. So first of all, we need as a input FDF, and the another input file we require PSF, means the pseudo potential file. So let me talk about briefly all these things. So how potential can be taken care in SIESTA? In SIESTA, potential can be taken care with the help of the PSF file, that is the pseudo potential file. One thing, and another file that is needed, it is the FDF file. FDF file means it is the free data format file. It contains structural information. I shared with you a file, a folder that contains FDF files and the various pseudo potentials of various examples which I am considering. So what and how this PSF file can be generated? This PSF file can be generated either you will use tested pseudo potentials, or you can generate your own pseudo potentials. And to generate pseudo potential, you need to install another package. That package is known as Atom program. You have to install this Atom. I shared also with you that how Atom can be installed. It was little bit tedious, but if you have some patience and you have certain command or certain idea of Linux commands, then you can easily install all these. Right? So that means if you want to generate your own pseudo potential, then you have to install the Atom code, and if you use other pseudo potential files which are already available on the various website, but the problem with those pseudo potential is that those pseudo potentials are not relativistic. Those are the plain pseudo potentials. So if your system is spin polarized, means if your system has magnetic characters, then you need a relativistic pseudo potentials. So for that you must know that how pseudo potentials are generated. So I shared with you a link. Let me show that with you right now also. So this is the Atom installation. This is the link of YouTube in which I told you, I told that how Atom code will be installed and pseudo potentials are generated. I will leave this presentation here with Dr. Manish, so that he will share with you, so that you can go through all these links, because in 1.5 hours it's very difficult to tell each and everything about it, right? So there is a one playlist on the YouTube, basic installation of SIESTA, and some examples I have mentioned there. And a few days back there is an international workshop in my institution, so live recordings are also there, so I will also share that with you. Means few links are there. So this is the SIESTA installation. This is split into two parts, and this is the Atom installation. Then this is the playlist of SIESTA, and in this I have covered SIESTA and its basics, right? So let me now talk about all these things practically, how things can be done practically. So I will be comfortable in SIESTA, and let us check whether on your system SIESTA is installed or not. Say on my system, SIESTA, I have installed SIESTA in different folders, different versions. So on my system, SIESTA, if I put a command SIESTA and it will work for me. Say Is it happening on your systems? That's great. That means SIESTA is working for you. And I have shared with you only the serial installation of SIESTA, not the parallel installation, right? So I told you that it needs PSF file and another is the FDA file. So let me share with you first of all the FDA file. So if you go to the folder in which you have downloaded the chipped file, so this is the folder which I shared with you participants, right? So please unzip it and go inside it. So I opened a terminal here. Let me open terminal here and go inside it. So let me first of all go inside the H2 molecule. This is a very beautiful example and it contains few files. One is FDF file, FDF data, and another is h.fdf, right? So FDF data is basically it is a template of this one, and here there is a script evslat.sh. It's basically a script, right? So what this script will do for us, first of all let me talk about it. So I am opening this script. The very simple script. So what is there? It's a shell script, and if I try to look at this, so here it is 0.5 and then it is 0.5 oh sorry, it is you can change it. Let me go into the insert mode. Yeah, say I am running simulation. Say I want to run a simulation from 0.5 to 5.0 in a small steps of 0.02. It's basically separation, right? And it is a I is a variable, and what it will do, it will go inside the FDF data, means it contains structural information, and I is replaced by LATT inside the FDF data, and then it will make for us different FDF files, and this is a command to run the simulation. This is information of the input file and it is the information of the output file, means it will make a output file with this name for us, and done. This is a simple script. Otherwise what you will do, you have to make the different FDF files for different lattice constants. In the earlier lecture in the morning, Ahluwalia sir told that, say there is one hydrogen atom and there is another hydrogen atom. What I will do, I will bring this hydrogen atom towards this hydrogen atom. So what will happen, it will show attraction, and after a particular distance it will show a repulsive forces. So that means this is the point at which bond formation will be occur. So first of all let me estimate this thing. So for that what I will need, I need different FDF files and I will run the simulation, and for that it will gives me the energy dot dat and structure will automatically gets optimized. So let me run this simulation first of all. So that means here there are two files, one is the FDF data and another is the h.psf, and I am using a script. because otherwise I have to change the things manually. So let me first of all talk about this FDF data file. Different codes have similar information, but syntax will be different. So here it is the system level, H2, number of atoms. Our system contains 2 atoms, and how many species? Only one type of species are there, that is hydrogen. And here one atom is placed at where? 0, and another is, it is a variable. I defined it earlier with the I in the script. Otherwise you have to change this LATT. So I am using LDA, exchange correlation functional, and spin polarized will be false. So it's a simple calculation. Let me run it. So what I will do, so it's a script, I want to run this script, and I have mentioned the path. So simply what you will do, sheb slat.sh, and it will run the simulation for me. So please do it. If you have any issue, then I will try to resolve that. And if I go to the folder, see, and it's still running. So let us have a look at output file, or let me, yeah. So what this script will do, it will make a file for us first of all with the h2.0.50.fdf, and it will run it, and it will gives a new file .out file. So let us have a look at out file. So first of all, let me talk about this out file. Say here is the, initially it gives us that what type of input file you are giving, and then these are the basis sets. I will talk about it later on. And if you seriously want to learn SIESTA, then I will help you out later on online mode. We can, in a week we can spare 1 hour, so that you should learn that how SIESTA will work, because in short span it was very difficult to told each and everything. So if I try to look at it, say these are the force calculations, means it had calculated the forces, then in the end, yeah, these are the forces, this is the stress tensor, and in the end you will get total energy, because ultimately what we are getting, okay, there is some issue with it. Okay, gedit. Yeah, here it is, it contains total, it's a total energy. So let me go back to now the Schrodinger wave equation, that what Schrodinger wave equation will do for us. So in Schrodinger wave equation, if I try to look at it, H psi is equal to E psi, it is the Schrodinger wave equation. So what we are doing in all the DFT codes, we are basically solving Schrodinger wave equation, either relativistic or non-relativistically. So when we solve Schrodinger wave equation, so what we are calculating? We are calculating energy. So energy is with me. This is the total energy of the system, particular say. So in every file, in every output file, command. So what I will do, I grab a line containing total space equal to I want to extract this data from out file, so I will write down star dot out, means it will grab this from every, and I want to paste it in certain file. So say t energy dot at. So there is a file. Let me check whether this energy.dat file is formed or not. Yeah, ls energy.dat file is already there, or ls star.dat. Yeah, this file is there. So let me open it in gedit. See, this is a file which contains so I want to delete rest extra lines. So I will delete it, h2 dot, I replaced it, then dot out SIESTA, because I want to plot the data. And I saved it, and let me try to plot it. I can plot it with the help of XM Grace. So XM Grace energy.dat. See it. So there is a minima. It's at roundabout minima will be at roundabout 0.80. So that means मैंने कोई इसमें कोई स्पेशल कुछ नहीं किया, सिंपल अप्रोक्सीमेशन यूज की. आई यूज्ड LDA और कोई फ्लैग के साथ अभी प्ले नहीं किया, और इसने अपने आप इसको ऑटोमेटिकली ऑप्टिमाइज करके मेरे पास दे दिया. एंड इंटरेस्टिंग थिंग विद द सिएस्टा इज दैट you can do calculations for 3-dimensional system, 2-dimensional system, 1-dimensional system, even 0-dimensional systems. But it was very difficult. I have never seen papers on 1-dimensional or the 0-dimensional system with other codes, because that will require a more memory. High-end machines are required. But for SIESTA, you can switch from 3-dimension to 2-dimension, 1-dimension, even 0-dimension. And that is the advantage of this code. And you can do spin polarized calculations. Right? So, have you reproduced this result or graph or not? How many of you reproduce this? Calculation is running or over? कितने सिस्टम्स पे कैलकुलेशन चल रही है? क्या हो रहा है? क्या एरर आ रहा है? लेट मी चेक इट आउट. नहीं, आप ऐसा करो, जहां जो फोल्डर मैंने दिया है, आप फोल्डर दिया, मैंने फोल्डर दिया है, हाँ, उस फोल्डर में जाइए. H2 का फोल्डर होगा उसमें, वहां जाइए आप. सिएस्टा इंस्टॉलेशन नहीं हो रही है. ये कई बार क्या होता है सिएस्टा में, क्या हो रहा है, अगर हम wget कमांड से या wget कमांड से डाउनलोड कर रहे हैं, तो उसका जो ऑब्जेक्ट डायरेक्टरी है, उस डायरेक्टरी में वो पूरी डाउनलोड नहीं हो रही है, उसमें सेटअप फाइल नहीं मिलती है. तो अगर आप उसको डायरेक्ट डाउनलोड करो, मैं अभी बताता हूँ आप लोगों को सिएस्टा कैसे इंस्टॉल होगा. ये गिट लैब पे जाएंगे, ठीक है, यहां पे अब यहां पे सिएस्टा का वर्जन ये कर लीजिए, स्टेबल जो है 4.0 कर लीजिए. 4. या 4.01 कर लीजिए. जैसे ये मैंने यहां से सिलेक्ट किया, ठीक है, ये हो गया. अब आपने इसको क्लोन नहीं करना है, सिंपल यहां पे डाउनलोड कर लीजिए. बिकॉज जब हम गिट क्लोन करके या क्लोन करके डाउनलोड करते हैं तो कुछ फाइल्स इसकी डाउनलोड नहीं होती है. तो ये मैंने इसको डाउनलोड कर लिया. targz करना है, जिप फाइल, इट्स ऑल अप टू यू. मैंने targz फाइल, यहां पे डाउनलोड्स में चला जाएगा. ये डाउनलोड हो रहा है. इट्स डाउनलोडेड. डाउनलोड्स में गया मैं, एक काम करते हैं, लेट मी डू वन थिंग. मैं डेस्कटॉप पे फोल्डर क्रिएट किया, mkdir JNU. मैंने इसके अंदर काम करना है, राइट. आई गो इनसाइड इट. ये JNU फोल्डर मैंने क्रिएट कर लिया. अब डाउनलोड्स में सिएस्टा था, राइट, इट वाज इन द डाउनलोड्स. सो मैं क्या करूंगा, कमांड लाइन पे, कमांड को समझने की कोशिश करना सभी ने. कमांड दी मैंने कॉपी cp, इसका मीनिंग है कि मैं होम में चला गया. इट मींस कि मैं कहां हूं, नाउ आई एम इनसाइड द होम. होम में डाउनलोड्स फोल्डर है. मैं कमांड लाइन पे बता रहा हूं, आप माउस से क्लिक करके भी कट पेस्ट कर सकते हो. ये डाउनलोड्स में गया मैं, और यहां पे ये सिएस्टा था. ये 4.0, बड़े सारे वर्जन्स हैं. सो मैं 4. या इसको करता हूं जो मैंने अभी डाउनलोड किया, B4. जो आपने डाउनलोड किया आप उसको कर लीजिए. ये वहां से कहां आ जाएगा. सो सी, लेट अस लुक एट दिस कमांड. इट मींस कि मैंने क्या किया, cp कॉपी करना है. कहां से, इस कमांड का मतलब है कि मैं होम में चला गया डायरेक्टली, जहां मर्जी बैठा हूं. जैसे मैं ये सिंबल यहां पे लगाऊंगा, देन मैं इमीडिएटली कहां पे चला जाऊंगा, होम में चला जाऊंगा. एंड देन डाउनलोड्स में फाइल पड़ी हुई थी इस नाम से, वो मैंने उठाई, कहां पे लेके आनी, जहां मैं अभी बैठा हूं. सो कहां पे बैठा हूं? डेस्कटॉप में JNU फोल्डर के अंदर. तो स्पेस देके ये सिंबल डॉट लगा देंगे, फुल स्टॉप, स्पेस देके. सो दैट मीन्स मैं जहां बैठा हूं वहीं पे जाके फाइल आ जाएगी एंड इट्स देयर. ls करूंगा मैं लिस्ट की, ये मेरे पास SIESTA यहां पे आ गया. अब मैं क्या करूंगा, इसको अनजिप करना है. tar-xvf फाइल का नाम, और ये देखो अब ये अनजिप हो गई. नाउ यू गो इनसाइड द SIESTA. ये मैं इसके अंदर गया, SIESTA के अंदर OBJ में जाएंगे, ls करो, ये रीडमी फाइल है. अब sh:// src obj setup.sh. कंपाइलेशन सेटअप डन. अभी भी इसमें कुछ मिसिंग है. इट मीन्स ये पूरा डाउनलोड नहीं हो रहा है. जस्ट मिनट, ये पैकेज पूरा नहीं आ रहा है. लेट मी रिमूव इट. लेट मी अगेन कॉपी. सॉरी, इसको ट्राई करता हूं. ये हो नहीं रहा. मैं एक मिनट फिर से चेक करता हूँ. लेट मी शेयर विद यू द प्रॉब्लम. एक्चुअल प्रॉब्लम क्या आ रही है. ये इंस्टॉलेशन का मैं बाद में अपलोड कर दूंगा वीडियो आपको, ठीक है. आगे प्रोसीड करते हैं. राइट, सो H2 मॉलिक्यूल हमने किया एंड देन उसके बाद हम आते हैं किसी और सिस्टम पे. जैसे ये गोल्ड का सिस्टम था मेरे पास, ठीक है. अब गोल्ड की मैंने अलग अलग फोल्डर्स यहाँ पे क्रिएट किए हैं. इस पे 2D पे तो नहीं जाएंगे आप लोग, 2D पे जाने की जरूरत है. 3D एंड देन 3DSC, 3D FCC, 3D BCC, right? So let us understand first of all structure. So gold is basically a FCC lattice. FCC structure है gold का. So what is FCC? सो इन FCC बिकॉज हम क्या करते हैं, हम कोशिश करते हैं प्रिमिटिव मोड में जाने की. प्रिमिटिव सेल अगर हमारे पास होगा देन नंबर ऑफ एटम्स विल बी लेस एंड दैट विल बी बेटर चॉइस रादर देन टेकिंग एक्चुअल सेल. सो वन एटम इज सिटिंग हियर, अनदर इज हियर. इस तरह से हर एक कॉर्नर पे एक एक एटम बैठा हुआ है. सो दैट मीन्स ओवरऑल कंट्रीब्यूशन फ्रॉम द कॉर्नर एटम इज 1. और एक एक एटम कहां बैठा हुआ, हर एक फेस पे बैठा हुआ है. सो कितने फेसेस हैं, 6 फेसेस आर देयर, सो दैट मीन्स दे उनका कंट्रीब्यूशन कितना 1/2, सो दैट मीन्स 1 फ्रॉम कॉर्नर and 3 atoms contributing from face. It's a very simple idea. So, and what are the lattice vectors of FCC? FCC किटल में बड़े अच्छे से mentioned है. So FCC के क्या होंगे? So that means what is the nearest neighbor? Let me connect to that. So जो nearest neighbor है मेरे पास, जैसे सपोज करो इसको मैं सेंटर मान लेता हूं, सो फ्रॉम हियर इट इज द फर्स्ट नियरेस्ट नेबर एंड इट इज द अनदर नियरेस्ट नेबर. इसको मैंने क्या किया, इसको मैंने लैटिस वेक्टर कंसीडर कर लिए और इसको कंसीडर करके मैंने 3 क्रिस्टलोग्राफिक सॉरी ये लैटिस वेक्टर्स जो थे ये ड्रॉ कर लिए बाय कंसीडरिंग नियरेस्ट नेबर्स. अब मैं आता हूं जरा, ये एटम कहां पे बैठा हुआ है? इट इज सिटिंग इन द वन फेस, से इट इज एक्स एंड इट इज वाई. अगर ये एक्स वाई है तो क्या इसके लैटिस वेक्टर्स क्या हो जाएंगे? 0.5, 0.5 एंड 0. और इसके क्या हो जाएंगे? दूसरे के 0.0, 0.50 एंड इट इज 0.5. और तीसरे के लैटिस वेक्टर्स क्या आ जाएंगे? 0.5, 0.0 एंड 0.5. ये मेरे पास लैटिस वेक्टर किसके आ रहे हैं? दीज आर द लैटिस वेक्टर्स ऑफ एफसीसी. एंड इफ आई कंप्लीट ए सेल, प्रिमिटिव सेल, so what I will do to do that, ये देखो the cell has been almost completed, ये this way. ये सेल मेरे पास कंप्लीट हो जाता. तो ये जो सेल मेरे पास अभी ड्रॉ हुआ this one, ये कौन सा है? it is the primitive cell for what? primitive cell for FCC lattice. so ये जो FCC था एक्चुअल FCC में कितने एटम्स थे? टोटल नंबर ऑफ एटम्स विच आर कंट्रीब्यूटिंग इट इज 4. बट इफ आई लुक बैक हियर, सो यहां पे कितने एटम्स कंट्रीब्यूट कर रहे हैं? ओनली 1 एटम इज कंट्रीब्यूटिंग. सो अब मैं इसकी एफडीएफ फाइल आपके साथ शेयर करूंगा कि एफडीएफ फाइल में इंफॉर्मेशन कैसे बैठी हुई है. ये स्टैंडर्ड एफटी फाइल्स है, मैंने कुछ पैरामीटराइज करके इनको खुद बनाया था अलग अलग से. जैसे यहाँ पे इनपुट फॉर सिएस्टा, सिस्टम नेम, ये सिस्टम लेवल मींस नंबर ऑफ स्पीशीज, ये 1 तो 1 है, अगर 2 है तो 2 डिफरेंट स्पीशीज आएंगी, बट यहाँ पे एक ही स्पीशीज है तो ये 1. एंड एटॉमिक नंबर आ गया 79. एंड आफ्टर दैट एटॉमिक कोऑर्डिनेट्स हम क्या देके चल रहे हैं? दीज आर द फ्रैक्शनल कोऑर्डिनेट्स. एंड ये क्या है? दिस इज बेसिकली द पोजीशन. सो आई एम कंसीडरिंग ओनली 1 एटम पर यूनिट सेल. पर यूनिट प्रिमिटिव सेल में मैं सिर्फ एक एटम लेके चल रहा हूं. बट इफ आई गो बैक टू डायमंड, तो डायमंड में मेरे पास एक की बजाय यहां पे 2 एटम्स आते हैं. और ये क्या है? दीज आर द लैटिस वेक्टर्स. LC क्या है? इट इज द लैटिस कांस्टेंट. एंड लैटिस कांस्टेंट की वैल्यू मैं कहां से रीड करवाऊंगा? स्क्रिप्ट से, जो स्क्रिप्ट मैंने आपके साथ शेयर की हुई है. ये स्क्रिप्ट है. दिस इज द स्क्रिप्ट, राइट. सो इस स्क्रिप्ट में मेरे पास 3.0 से लेके मैंने 15.0 तक सिमुलेशन रन की इन स्टेप ऑफ 0.1. और अगर मैं लैटिस कांस्टेंट चेक करूं गोल्ड का लैटिस कांस्टेंट आई थिंक 4.08 या 4.09 होता है, एक्सपेरिमेंटल जो वैल्यू है. और अगर आप सिमुलेशन करो तो 4.12 के आसपास आपको मिनिमा मिलेगा. तो स्क्रिप्ट को आपने रन करना है. यहाँ पे मैंने सिएस्टा PAR किया हुआ, इट मींस मैंने सिएस्टा को पैरेलल इंस्टॉल किया हुआ, तो वो उसकी कमांड है। बट आपने PAR की बजाय, जस्ट नोट इट, PAR की बजाय सिएस्टा अंडरस्कोर PAR की बजाय आपने क्या रखना है, सिंपल सिएस्टा, बिकॉज आई हैव इंस्टॉल्ड इट इन द पैरेलल बोर्ड, बट आप लोगों ने नहीं किया हो, बिकॉज पैरेलल में इंस्टॉल करने में थोड़ा टाइम लगता है। इसको अगर मैं रन करके बताऊं तो उसी तरह से स्क्रिप्ट रन होगी ./evslet.sh, evslet.sh, ये कमांड आप स्क्रिप्ट रन करने के लिए ये कमांड है, ये इस तरह से, एंड इट विल डू सिमुलेशन फॉर मी। सो मैंने ऑलरेडी की हुई है कैलकुलेशंस। ये देखिए बहुत सारे स्टेप्स हुए पड़े हैं, इनको मैं ओपन करके, ग्रेप टोटल एनर्जी मुझे उठानी है इक्वल टू एंड स्टार डॉट आउट टी एनर्जी डॉट डेट, ये आ जाएगी। उसी तरह से gedit में जाके या सो एक्स्ट्रा जो डाटा है दैट आई हैव टू डिलीट। चलो मैं बी एडिटर में इसको डिलीट करता हूं। या delete it। सेव कर लो। आप कोई भी ग्राफ प्लॉटिंग टूल का यूज कर सकते हैं। मैं यहाँ पे XM Grace का कर रहा हूँ, यू कैन आल्सो यूज GNU Plot और एनी अदर सॉफ्टवेयर। सो XM Grace, द फाइल नेम इज द energy.dat। सो ये देखो यार, जस्ट लुक एट इट, ये मेरे पास यहाँ पे जाके इट्स 4.10 के आसपास यहाँ पे मिनिमा आ रहा है। एंड another very interesting thing which we are getting out of this graph, it's like Lennard-Jones potential. So here you are getting minima, so what I will do, if I try to look at this, means when I am bringing further apart gold atoms from each other, the energy is converging, and if I try to look at these values, say this is one value of energy is here and another value of energy will be here, and if I take the difference of these two values, then this gives me the binding energy or cohesive energy. So this is a way that how do we calculate the binding energy of the material. But I did calculation for BCC, FCC and simple cubic, because computer doesn't know what type of structure it is actually having. So it gold may exist in FCC, BCC or simple cubic. So I run calculation for all these three, and how do I decide that in which structure it is existing actually in nature? That was decided with the help of energy. So see here, for BCC it contains energy underscore BCC dot dat. Similarly for others also, this one, and for this also. So let me plot all these. So what I will do, I will open a terminal and then I will go to the XM Grace and go here, data, import ASCII, and here I am sitting inside the energy SC.dat, means energy for simple cubic. So I just plotted it, and after that I again go back. After SC I go to the FCC I have taken, because I run these simulations already, and then I go back again. Let me go to one is, yeah, it is BCC. Now see these three different graphs. This is a very beautiful demonstration. This is one plot. This is for simple cubic, and this is for FCC, and this is for what? This is for BCC. So let me compare. So this is the lowest most energy. So if I compare these three, so that means this gold is existing in FCC structure, because this is for simple cubic and this green is for BCC. So that means how energy help us to predict the nature of the material. That's what we have observed here. So two things we are observing here. So one is the predicting nature, estimating the lattice constant, and lattice constant estimation, and after that we have also estimated the bond length of the hydrogen molecule. Even you can do simulation with any molecule, even you can take complicated structure, then you will also get that relaxed and you will get its properties. Even how charge is distributed, that you can also know. In the morning lecture, Aluwalia sir told the say the bond length of hydrogen atom, and basically the contours which we are getting, the plots, those are basically charge density plots. Three-dimensional charge density plots are there, and those are plotted with the help of a GNU plot. So until now, any question, and after that I will proceed towards the band structure. So now it's sure that this gold is existing in FCC in the FCC phase. So for that, what I will do? I will do calculation for the band structure for the estimated lattice constant. So this is for this. This is the simulation which I run for it. So one structure is optimized with us, So the lattice constant which is there with us, it is the 4.10. I have taken the relaxed structure, and the exchange correlation functional which I am using, it is a GGA, and PBE-SOL is the exchange correlation functional, means author, and spin polarized is false in this case. And these are some parameters. These parameters are basically which I have chosen, these are optimized parameters. DM mixing rate is a very important parameter. If your simulation will not converge, then you can play with this parameter, DM mixing rate. Sometimes simulations will not converge, then you can change this value. First of all, you can try with the 0.05, 0.02, and later on if it's still you are facing certain issue with the convergence, then you can change this parameter to 0.01. But it's better if you use this parameter as 0.10. If it will converge, then that will be better. But for large system, sometimes we face certain issues, then try with the smaller parameter. Here you can do calculation for the ferromagnetic and anti-ferromagnetic. I have mentioned the flags with comment. Then mesh cutoff, it's better if you use mesh cutoff 300 Rydberg. Sometimes people will try with the default parameters. If you take default parameters, then your results may change. So better you test the energy convergence parameter, then decide all these things. I mentioned these in my YouTube lectures also. K mesh cutoff is another very important parameter, and another is the this parameter, PAO basis size, DZP, double zeta polarized basis set we are using. Better if you use this is one parameter, and better you take this PAO energy shift from 20 milli electron volt to 50 milli electron volt. If you take higher values, then things may run fast, but results may not be reliable. So better if you take 20 milli electron volt to 50 milli electron volt. I am discussing very important parameters with you, and if you do phonon calculations, then you can change this DM tolerance to -5 or the -6. And another very important parameter is the K grid cutoff and K Moncost pack. So it's basically a three-dimensional material, so I am taking it as the 15 by 15 by 15. But if you change the dimensionality, then these parameters will change. And this is the projected density of state. By default its value is 0.2, but if we take 0.05 and in place of 2000 here we will take 4000, then data points are good enough so that it will show actual results. But if you take smaller number of points, then sometimes band structure shows system is semiconducting, and in density of states you will see it looks like a metallic. So that's only because of this parameter. And if your structure is optimized, there are two different possibilities. This is a very important parameter. MD type, what type of molecular dynamics you are running. So it's a MD type of run, it is CG. CG means conjugate gradient method you are using for the optimization. And here if you have a relaxed structure, means relaxed cell parameters, then you can run simulation for the 0 step. But if you are running simulation for molecule, then for molecule you have to run or you have to take number of CG steps, 1000 or the 2000. And once structure is optimized, it will automatically close the simulation. So that's it regarding this. These are the few very important parameters. So after that, certain files are there with us. So it contains density of state information. There is another very important file, that is PDOS. PDOS means projected density of states. So you can see that which orbital is contributing for the density of state. Say S orbital, D orbital, F orbital. And another is the dot bands file is also there. It's not there. What's the reason? Let me go back to AU dot FTF. It's not there. What is the possible reason? Oh, I have not mentioned the high symmetry points. High symmetry points are also very important. So let me go back to there. How do we decide the high symmetry points for any code? In SIESTA there is a file xv, so I have to change the file xv to xsf. I will change its format, xv to xsf. It's a command, so I've just mentioned it, and name of the system is this one, AU, and again xsf file is also there. Let me go back to xkristen. There is another tool, that is xkristen. If you have not installed, then try to install that. So command to install it is sudo get install xkristen. So you can install it, but on my system it is already installed. So I will give a command xkristen -- because I want to see the xsf file, and the name of the xsf file is this one. So this is the structure of gold which I am looking. See, you can see it in this primitive mode also, or in this mode also. So go to the tools, because I want to see the high symmetry points. Go to the K path selection, say it is the Brillouin zone, and from here you will decide the high symmetry points. This is again very important point. When you switch over dimensionality from 3D to 2D and 2D to 1D, then you have to choose K points very carefully, otherwise your band structure will not be reliable. So what are high symmetry points? Let me go to the website. Yeah, high symmetry points. Yeah, Brillouin zone. Say it is the FCC lattice, and these are the its high symmetry points. So first of all, this gamma is what? Gamma is the center of the Brillouin zone, and for FCC, middle of an edge joining two hexagonal faces. It was mentioned here. So for your system, what are its values? So that how they can be decided. So say this central point is basically this is gamma point. I have mentioned 0, 0, 0, and then what is K? K is what? K is this point. You can see middle of an edge joining two hexagonal faces. So this is K. The coordinates of K are, so 0 0 0, and it is 0.375 0.375 0.375. This is for the K. And after that, center of an hexagonal face. So the center of the hexagonal face is this one, this point. So its coordinates are, this is L, and its coordinates are 0 0 0.5. Similarly, if you go to the U is what? Middle of an edge joining hexagonal and the square face. So this point is U. So 0.375, 0, 0.625. So these are the different hexagonal. These are the different high speed tubes. Similarly, you can choose others also. W is the corner point, center of the square face. Say it is X. 0.5, 0 and 0.5, and finally you can take again gamma. So it is 0 0 0. So this is a way that how high symmetry points can be taken for different structures. It's helpful for those if you want to design a new system. For that it will help if you decide this manually. So once structure is there, then Brilliant zone is also with you, and that can be taken or seen when you will convert XV file to XSF file, right? So these are the high symmetry points. So let me now put high symmetry points in SIESTA, in what we call FDF file. So these are the high symmetry points. This is the block which you have to take. You can also take screenshot of it also. I am just copying these. Because it was not given to you. So when I run this simulation, just save it, and there is some error. Let me go back. Yeah. PTK grid mount cost back. Let me run it, then let me check it out. So again, the command is SIESTA au.fdf t au.out, means the out file, name of the out file. Let us see whether bands file will be formed or not. And let me show you one more thing. Yeah, so it's SIESTA 4.1. In SIESTA there are some directories. So one is the sudo, it contains sudo potential. You can generate inside it sudo potential, means you can install atom code inside sudo. And then there is util. Util is a very important directory. In util there are different utilities. Bands is used to plot the band structure. Then COOP, it's for the charge density analysis, that how charge is transferred. Denture is also for the charge density plots. Then EIG to DOS means how from .eig file can be converted so that density of states can be plotted. Then another is important is the Vibra for phonon calculations. Optical for optical properties. You can plot dielectric function, real and imaginary part, reflectance, refractive index. All these things can be calculation can be done with the help of this tool. Then there is another very important directory, that is contrib. So you go to the contrib. Just a minute. Again, let me go back. Yeah. So I am talking about contrib. So cd contrib, or you can compile all these small tools with the help of a command /build all.sh. This is a command to compile all these tools, right? And after that, let me go to the contrib. A Postnikov. So Postnikov has given certain tools. You can compile these with the help of a command make. Sorry, SIESTA is not installed here, because for that you need to install. So basically here is a tool xp2xsf. So when you compile this, then it will make a executable file with green color, that is xv2xsf, and I have used that tool also. Similarly, there are another tools. fmpdos is also there. fmpdos is, yeah, this is fmpdos. With the help of it you can plot density of states, projected density of states. And let me go back again. Here, if you go to the bands and if you compile it, again there is some issue with the SIESTA installation, but on my system I have already compiled it, not in this folder. Utils, yeah, just see it. I have compiled it already. So glue bands is a tool which is used to extract data from .bands file. So what you will do, either you will give the path of this tool, or you will copy this from here to this tool GNU bands, from here USR local bin. सो इसका बेनिफिट ये, आप जहां मर्जी बैठे हो वहीं से आप इस टूल का यूज कर सकते हो, अदरवाइज आपको पाथ देने की जरूरत पड़ेगी. एंड you are entering into the root directory, means us/usr is a root directory, you are entering into it, so it will require a permission, root permission. So sudo command will be given, and so that it gets copied to there, and then enter, and it will require a password. So from everywhere you can give that command. Let me go back again. So I think our simulation is done. जो भी हमने गोल्ड की सिमुलेशन चलाई थी, दैट वाज डन. सॉरी, yeah, it's done. See, dot bands file is also there. This is the dot bands. So if I try to plot this dot bands file, then I cannot plot it directly, because it is in the different format. So what I will give a command, gnu bands less than symbol, and then input file au dot bands t bands dot dat, it's the new name. So go to the gedit, sorry, now simply xm grace, or you will do it's one thing. And there is another command, is that gnu bands dash f bands underscore f कर रहा हूं मैं इसको. These are the two different commands, right? So मेरे पास दो फाइल्स यहाँ पे बन गई, star dot dat, sorry, star dot dat. These are the two files. So let me try to plot these two files first of all. So go to the xm grace, go to the data and then import. It's a bands dot dat, एक बैंड स्ट्रक्चर ये आ गया, एक इसके साथ और प्लॉट कर लेते हैं. सो आई गो टू द हेयर, edit arrange graphs, and then duplicate it. I duplicated it. There is another graph overlapping over it. I separated it out by dragging. जस्ट ट्रैक किया माउस से क्लिक करके कॉर्नर पे. इसको डाटा को मैं डिलीट कर देता हूँ. इसमें मैं दूसरा डाटा इंपोर्ट करता हूँ, किल डाटा, राइट, और दूसरा ये मैंने सिलेक्ट किया था, एंड इट विल गोज टू हियर. एंड लेट अस ट्राई टू लुक एट दिस नियर द फर्मी access properties. So say let us take it from -10 to 10 by axis, -10 to 10. -10 to 10, let us take it from -4 to 4, because it's very important at which part you want to focus. This is a very important thing. सो ये दो बैंड स्ट्रक्चर आ गए. मैं इनमें डिफरेंस बताऊंगा, व्हाट इज द डिफरेंस बिटवीन दीज टू. जो एक्चुअल गोल्ड का बैंड स्ट्रक्चर है दैट इज लाइक दिस, नॉट लाइक दिस. सो व्हाट आई डिड, जो मैंने GNU प्लॉट पे GNU बैंड्स पे कमांड दी थी, द कमांड इज बेसिकली दिस वन. इट इज GNU bands -f and then name of the input file and then output file. So what it did, it shifted the Fermi energy. It shifted the Fermi energy automatically. Otherwise you have to shift the Fermi energy manually. So let me go back again. Say it is the Fermi energy -7.864. So what I will do, I will go here again, data and then transformations, evaluate expression. I selected this data and then also this whole data, and then I shifted y is equal to y. Oh sorry, there is some issue with equal to. So for that what I will do, there is some problem with equal to. Okay. Let us see whether I can copy it from here somewhere else or not. But copy this will not work in, I think, XM Grace. There is some problem. Yeah. No, it cannot be done here. So here you have to give y equal to just a minute, y equal to y plus the value of the Fermi energy in magnitude, and then both the graphs will look identical. So it is the actual band structure. And another thing, you need to plot the high symmetry points. So high symmetry points are also written here in the end. These are the high symmetry points coordinates, so you have to mention these coordinates are also. So this is a way that how band structure can be plotted with the help of SIESTA. So once band structure is there with us, we are able to predict the nature of the material, whether it is the semiconducting, metallic or magnetic also.
So I have a question that is there any difference between symmetrical point and high symmetrical point? Like how do we make a decision? Is there any difference, or is it just that any point which is symmetrical about the crystal, we can call it as a high symmetrical point?
High symmetry points and the symmetry, these are the two different things.
That's what I'm asking.
Yeah,
actually,
because high symmetry points are basically some special points, say at the edges or in the corners or in the center of certain. Because have you seen the
yes, I saw that.
Brilliant zone?
Can I
Yeah.
say something? Symmetry points we work in a direct space.
Direct space.
And high symmetry points we
In the
choose in a brilliant zone.
Brilliant zone means
It's
the
a
reciprocal space, right?
Generally, we consider, I think, the high symmetry
High
point in
symmetry point.
irreducible brilliant zone.
Yeah.
Yeah.
That is when we
Inside the
are
brilliant zone, we specify irreducible brilliant zone. But some points are there which are repeated. Means you will see the similar type of the bands on those points. So means symmetry point may be many, but
High
the
symmetry
high symmetry point will be only one.
limited one.
And another thing, that different materials have different high symmetry points. Means whether it is FCC or simple cubic. Oh, sorry, it's there. See, for simple cubic they are different, And for FCC they are different, for body centered they are different, for hexagonal they are different, and for two dimensional they are different, and for one dimensional they are again different. So when we are switching from 3D to 2D or 1D, we try to make a cell, it's cuboidal type, not cuboidal type, because in two directions there is a vacuum. And another thing, there is a very important tool which is used to make SIESTA, FDF file for SIESTA, that is GDIS. This is GDIS. Say if I want to make a structure, I think the lattice constant of silicon is 5.42, it's round about it, right? So if I want to design a structure of silicon, and silicon has a diamond like structure, so what is a diamond like structure? Let me go to, first of all, try to understand the structure, because we must have the insight of the structure with. So it is FCC structure. So diamond like structure means it's a FCC lattice. This is one FCC, and say this is the body diagonal, and another FCC lattice is diagonally immersed into it up to the 1/4. So that means there is another, say it is the 1/4 distance. So if I make another, so this is another. So as I told in the earlier lecture, that one FCC, primitive FCC cell, contains one atom and its coordinates are 0, 0, 0. So when I go back to silicon, a diamond, then its second atom, which is the constituent of the second FCC lattice, which is immersed diagonally, so its coordinates will be 0.25 and 0.25 and the 0.25. So let me share with you now this diamond like structure or design. So I go to here, new model, and from here I go to the model editing. What I did, I added one atom, and let us call it as silicon. Enter, and then put it, say manually 0, x is 0, y is 0, and z is 0, right? And then I confined it in some box, and box must be, I go to the transformations, and it is say if lattice constant of say silicon, let me check it again whether it is this or anything else. Yeah, 5.5. I got it through simulation. It is 5.5 through simulation. It's a rough estimate. So I again go to the, GDIS. So 5.5 means it's 0.5, 0.5, so 5.5 means 2.75. It's 2.75, half of that, and here it is 2.75, 2.75, 2.75 and then 2.75. Yeah, then alter lattice periodicity, let us make it 3, and I can find one atom, and let me save it. SI underscore 1 dot, say SI dot FDF. I just make it. And let me go back. Yeah. Let me save it on the desktop. I just saved it on the desktop. Yeah, this is the file. Which I generated. So it contains only one atom. So what I will do, number of species will be 1 and number of atoms will be 2. I just make changes. One atom I placed here and another atom I placed here. 0.0, 0.0, oh sorry, not 0.0. It is 1/4 of the body diagonal. So it is 0.25. 0.25 and it is again 0.25 and it is a atomic species level. It is 1. This level you have to mention. So I saved it, and whether I have made number of atoms 2, yeah, it's done. So let me again go back to GDIS. Again open a structure. Yeah, it is there on the desktop. So but atoms are just overlapping. So what is the reason? There is some problem with the FDF. So what is the problem? That means if in place of this I will use fractional, it's a fractional. So when I will do it, I am again opening it. See, this is the diamond like structure of the silicon, and let me do one thing. I go to the images. See, this is a diamond like structure. So if I want to now switch from 3D to 2D and 2D to 1D, then GDIS will help you out, because when I am switching over from 3 dimension to 2 dimension, so that means in 1 dimension, in one direction there should be a vacuum. Say if we are sitting in this hall, it's very difficult for me to communicate with the persons who are sitting in the towards that side. But it's very simple for me to communicate with the persons who are sitting in this direction and this direction and in that direction. Right? So that means I have to create a vacuum so that the interaction will be least. It will not interact because all the DFT codes are working on the periodic boundary conditions. Means every cell is repeating itself in all the 3 directions. So if in one direction I am creating a vacuum, so vacuum either you can do it manually or with the help of GDIS. So say I just repeated it 4 by 4. I am just telling you that how things can be done. I go to the model editing, I make a supercell. So I confine it in a supercell. इसको मैं सेव कर लेता हूँ. Let us call it as silicon_1.fdf. अब सपोज आपने कोई डोपिंग करनी है, सिलिकन की जगह आपने क्या करना है, किसी एक एटम को हटा देना है. तो आप यहाँ पे इस एटम को सिलेक्ट किया, एक एटम सिलेक्ट करना है, दो नहीं, यहाँ पे दो हो रहे हैं, ये एक एटम आपका सिलेक्ट हो गया. गो टू द कंटेंट, ये सॉरी मॉडल एडिटिंग, ये सिलिकॉन का एटम था, इसको क्या करो सिल्वर से रिप्लेस कर दो. ये देखो सिल्वर आ गया. तो इस तरह से हम डोपिंग कर सकते हैं.
Sir, can you please repeat this part again? How
Ye-
do you convert one unit cell into
Okay.
series and then you
I just okay, let me do one thing. I go to this one, I just opened it. Just a minute. New model. I go to the just here and then open it. Okay, I have not saved that. Fractional. Just did it. फिर क्या प्रॉब्लम आ रही है? Okay. Open, go to the desktop. This has been modified. Okay. Let me go back again to the desktop. Where is this side.ft? Yeah. Oh, it's not saved. So let us call it as fractional. Let me again open it. Oh, FR is, yeah, spelling mistake. I go to here, images, and then repeat it. Say 5 by 5 or 4 by 4, whatever you want. I think 4 by 4 is better because it's, and then you go to here, it's model editing, make supercell. Earlier it's a single atom, sorry, two atoms per unit cell, but now we made it a supercell. So now you can make changes to the supercell. So you select one atom, any one atom where you want to dope. Say I have selected this one atom, and then I again go back to model editing. In place of silicon, I simply replace it with silver. So now it's a system in which silver is doped. So you can save it si_ag.fdf.
सर इसमें जो एटम को डोप कर रहे हैं तो फ्रैक्शनल डोपिंग भी कर सकते हैं, जैसे कुछ परसेंट, वो तो 100% हुआ सर एक एटम का सब्स्टिट्यूशन.
नहीं, fractional doping means you can do this calculation manually, that how many atoms do you have in a supercell and how many atoms of silicon you have replaced. That's the meaning of it.
एक यूनिट सेल में
Say if you are having, say let us say, because you are repeating it 4 by 4 by 4, so how many atoms do you have? So if you are replacing one silicon atom, then you can see the fractional change, you can do that calculation manually. I think software will not do everything for us. Some things we have to do manually.
सर ये कैलकुलेशन तो
सपोज 100 एटम्स है ना,
100 है,
रिप्लेस किया तो आपकी 0.1 होगी, 1 बाय
कैलकुलेशन तो बहुत बड़ा हो जाएगा सर उससे।
100 एटम्स
100 और मान लीजिए और कंपोजिशन चेंज करना होगा तो और बड़ा सेल सुपर सेल बढ़ाना पड़ेगा सर। तो
हाँ, तो सुपर सेल तो बढ़ाना पड़ेगा, या तो आपको एचपीसी की ओर स्विच ओवर करना पड़ेगा या सिएस्टा की ओर स्विच ओवर करना पड़ेगा। सिएस्टा 150 एटम्स तक से कैलकुलेशन कर लेता है। रिसर्च किट पे जाइए, वहां मैंने बड़े ज्यादा नंबर ऑफ एटम्स के साथ कैलकुलेशंस की, क्लस्टर्स के साथ कैलकुलेशंस की हुई है, तो सारी इसी लैपटॉप पे हुई है। इवन मेरा पीएचडी का काम खुद लैपटॉप पे हुआ है। आई थिंक आज हम बात करते हैं, स्टूडेंट्स आते हैं, सर ना स्पीड बड़ी कम है, इंटरनेट की बैंडविड्थ बड़ी कम है। मैंने और आलू वाले सर ने एक डोंगर लिया था, ईवीडीओ कार्ड आता था बीएसएनएल वालों का, 20 केबी पर सेकंड से ज्यादा उससे डाउनलोडिंग होती नहीं थी, और मैंने उससे कई बार उबंटू पूरा के पूरा ये डेवियन डाउनलोड किया था 3-4 दिन लैपटॉप लगा के। और मैं यहाँ की बात नहीं कर रहा हूं, मैं रिमोट प्लेस की बात कर रहा हूं, जहां कई बार लाइट भी 4-5 दिन नहीं होती थी। हाँ, एक बार तो 15 दिन नहीं थी सर्दियों में। हमें थोड़ा सा पेशेंस रखना पड़ेगा। हमें क्या हो गया कि हर चीज सॉफ्टवेयर ही करके देगा। एटीके या क्वांटम वाइज तो वेरी बेस्ट, बड़ा अच्छा एक टूल है। सेम वो आई थिंक 16 लाख का है, ये फ्री है। वो भी इसी जैसे सिएस्टा कोड वर्क करता है वैसे एटीके काम करता है, बट उसमें ग्राफिकल यूजर इंटरफेस है, यहां पे आपको ग्राफिकल यूजर इंटरफेस नहीं मिलेगा।
तो सर जो मतलब कि रेशियो को बढ़ा घटा कर, एटम को बढ़ा घटा कर अगर कुछ हम करते हैं तो उससे मटेरियल पे कोई इफेक्ट
नहीं, कोई फर्क नहीं। आप एक एटम को लेके बल्क चला लो, आप 100 एटम्स को लेके बल्क की कैलकुलेशन चला लो, आपका बैंड स्ट्रक्चर एक जैसा आएगा, कभी चेंज नहीं करेगा, कोई डिफरेंस नहीं आएगा। सो जब भी हमने कोई कैलकुलेशन करनी है, हमें मिनिमम नंबर ऑफ एटम्स लेके चलना है। जब हमने डोपिंग करनी है तो हम फिर उसको रिपीट करके उस तरह से फिर कैलकुलेशन करते हैं, कोई फर्क नहीं पड़ता, आप करके देख लेना, ठीक है। सो इसी तरह से अगर आपने वैक्यूम क्रिएट करना है, चलो मैं वैक्यूम करना थोड़ा सा मुश्किल जाएगा, बट लेट मी ट्राई इट। देखो मैंने ये क्या किया, ये सिलेक्ट किए थोड़े से एटम इधर के, ये डिलीट हो गए, ये डिलीट हो गए। बड़ा टेक्निकल चीज बता रहा हूं मैं आप लोगों को। ये देखिए, ये 2 डायमेंशनल लेयर बन गई सिलिकॉन की, जस्ट सी। एक साइड वैक्यूम है, रिपीट करूंगा तो क्या होगा, मैं ये अपलोड कर दूंगा अगर रिकॉर्डिंग अच्छे से हुई होगी, मींस इफ एवरीथिंग विल बी क्लियर। नाउ इट्स बिकम ए 2D मोनोलेयर। 1D बना लो, 1D बनाते हैं अभी, एंड देन आई विल स्टॉप। बिकॉज टाइम बड़ा कम था, मैंने कोशिश किया हर एक एस्पेक्ट को टच करने की। ये 1 डायमेंशनल बन गया सिस्टम, right? So if you want to make it 0 dimensional, then remove these atoms again. ये 0 dimensional बन गया आपके पास, it's a 0 dimensional system. GDIS पे आपको कहीं नहीं मिलेगा, ये 0 डायमेंशनल सिस्टम बन गया। देयर आर सम अदर टूल्स, एवोगैड्रो इज आल्सो देयर विद अस, वो भी काफी अच्छा काम कर लेता है हमारे लिए। इवन आप CIF फाइल को डायरेक्ट ओपन कर सकते हो GDIS में। आई थिंक आई हैव टू स्टॉप नाउ। इफ यू हैव एनी क्वेश्चन देन आई विल ट्राई टू आंसर दोस। थैंक यू वेरी मच।
Thank you so much, sir, for sparing your valuable time and enlightening the audience with the insightful hands-on training on SIESTA. I must say, on behalf of all the audience, you have put all your efforts but still the participants has to put some more effort